So yesterday we talked about thermodynamics, always a fun subject, and we ended up with talking about second law of thermodynamics, introducing entropy, and then introducing Gibbs free energy, and then we derived the condition for chemical equilibrium. And this is what it was. I rewrote this a little bit. I didn't like the way it was written. So we have, this is the chemical potential, which is equal to the partial molar Gibbs free energy. It has a temperature dependent part and a pressure dependent part. This was the condition for equilibrium. And then we just inserted this, here this thing, into this equation, and then here the mu I, you get these two terms. One is here on the left-hand side, one is on the right-hand side. And then this here looks very much like the reaction enthalpy, but it's the reaction Gibbs free energy. So we call it here just the reaction Gibbs free energy. I plug this in here, and then here on the other side. And then I can divide here by RT. I can take the exponential of this, and then I get exponential minus here this G over RT, and then the other side. Here we just have these partial pressures. And then you see here, and then this right-hand side here, we call this the equilibrium constant, Kp. P because it will lead you to the partial pressures here. And then you see that this left-hand side here just gives you the composition, and the right-hand side depends only on the temperature, depends only on thermodynamics. It's a pure temperature function. Temperature is fixed, then also the right-hand side is fixed. And then we looked at two examples, here one for an equimolar reaction and then one for a non-equimolar reaction. You have two molecules on the left, one molecule on the right, and then we saw if we then write the composition in terms of mole fraction, then the pressure ends up here in this expression. So that's, I think, where we stopped yesterday. And one thing that's interesting, I mean, this gives the composition in terms of the partial pressures. And, you know, I showed you can convert this to mole fraction. But sometimes it's interesting also to have the composition in terms of concentration. And so we can also here replace the partial pressure with the concentration. And then you see when I plug this in here, you know, I have a few species which end up, like here, which end up in the products end up in the numerator, the reactants in the denominator. And then here this RT term, if you have an equimolar reaction, then you have an equal number of RTs in the numerator, denominator, it goes away. It doesn't matter. But if you don't have an equimolar reaction, then this RT here divided by P0 term remains, but still now this here is then, or this is then the composition expressed in terms of the concentrations. And we call this quantity here Kp, equilibrium constant Kp, divided here by this RT to the power of basically the sum of all stoichiometric coefficients. We call this then Kc. That's just a different form of the equilibrium constant. Kc and Kp, and it's easy to convert them knowing the reaction. And Kc has a very special purpose. And that's shown here. So consider a reaction A plus B goes to C plus D. You know, I mean, you can have non-unity stoichiometric coefficients here, doesn't matter. Then I can write Kc for this reaction as concentration of C, concentration of D, divided by concentration of A times concentration of B, right? Like this. Now, I can also write the equation for the rate of change of the concentration of some species A here, let's say, A, which is then the consumption, or is then here the consumption of A is K forward times concentration of A times concentration of B, and then species A here is produced by the reverse reaction, which is then Kb times concentration of C, concentration of D, okay? Now, in equilibrium, we're worried about equilibrium. In equilibrium, the rate of change of all concentration needs to be 0, okay? Nothing can change anymore. And that means this needs to be equal to 0. And then you see I can bring here the Kb. So I bring this second term on the right-hand side. I bring the Kb here on the left-hand side. And then on the left-hand side I have, so let's first bring this on the other side. That is what we have here in equilibrium. And then I can bring the Kb here to the left-hand side. And I get this. And I bring the concentrations to the right-hand side. And I get this. And you see that this now, this expression is exactly the definition of Kc, okay? That's very interesting. Why? Because it says, I mean, K, the lowercase k here, the rate coefficient, that is something that relates to kinetics, how fast the reaction proceeds. The right-hand side here is equilibrium constant. It doesn't say anything about kinetics. It just says, where do you want to end up after infinitely long time, okay? But it turns out that the forward and the reverse rate coefficients, they are coupled by the equilibrium constant, okay? Very powerful, because if you tell me the forward rate, then I can tell you the reverse rate, okay? But just from equilibrium, just function of temperature. So for a given temperature, this we can compute easily from thermochemistry data. You give me a forward rate coefficient, I can tell you the reverse. And that, in fact, that's exactly how we do it. You know, in a code like ChemKin or FlameMaster, which I will show you, you specify only the forward rate and thermochemistry data, and then we compute the equilibrium constant, and we compute the reverse rate from that, so that we make sure that forward and reverse rate are consistent, because only then does the solution reach the correct equilibrium. Okay, so that's a function here that we often use in that sense. So this shows here Kp for a few different reactions, global reactions here. For H2 plus O2 goes to H2O, and then here O2 plus N2 goes to NO. And you see these have basically the opposite temperature dependence here. And then also here the water gas shift reaction, CO plus H2O goes to CO2 plus H2, and that is almost independent here of the temperature. This just to show you a few examples. Okay, so the equilibrium constant we can compute. Remember, it had 4 different terms. It had the reference, or the reference enthalpy part, the reference entropy part, the temperature-dependent entropy part, and the temperature-dependent enthalpy part. So these, the temperature-dependent parts, they were integrals, you know, CPdT and so on. And so the integrals, they are a little difficult to evaluate, okay? So, but we can try to approximate these, and you know, the approximation we get from this, it will give you, you know, something that is not super accurate. I mean, you know, it's an approximation, but it's something that you can use to do back-of-the-envelope calculations. Sometimes that's very helpful. So here's what we do. This is the equilibrium constant. You have this mu I0, and this, I mean, this chemical potential has 4 different terms, as I just said. These 2 terms, and then, I mean, here these reference terms, or the, let's say, the enthalpy of formation, entropy of formation, and then these temperature-dependent terms. And you see, so this is here, and then always you have the sum, and you have the, you know, the whole thing divided by RT. Now, if I plug this in here, I get a sum of 4 different terms, exponential of a sum of 4 different terms. I can write this as the product of 4 different exponentials, of course. And so these are the 4 different exponentials. The first one here just has the enthalpy divided by RT. And you see this here is nothing else than the reaction enthalpy, okay? So this here, I just call this reaction enthalpy, and we know how to determine this, you know, from these tables I showed you earlier. The second term here is now, you know, the temperature goes away, and this is actually just a constant. You see, this is a constant, this is a constant. This whole thing is just a constant for each species, okay? So I call this is a constant. And then the third term, here this term now, we want to assume that Cp is constant, and then I can integrate this, and I just get T minus T reference. And T minus T reference divided by RT, if I assume that the temperatures we're interested in, combustion temperatures, they are much larger than the reference temperature, which typically is like 300 Kelvin or 298 or something, then I can neglect here T reference, and then you see the temperature here cancels out. And then this term here also is just nu times Cp divided by R. And so also this here is just a constant, is roughly equal to a constant, approximation, okay? So, and then this last term here is basically a constant, or the exponential of a constant, times ln t. Now this factor here, the sum of this here, I can put this as the exponent above the temperature, right? And then we have exponential ln t to the some power, and I mean, or here, you know, this I put on the exponent, and then the exponent and the ln, they go away, and I just have t to the power of this sum here, okay? And so this is how I write this. These are two constant terms. I combine these and call the constant here, for each species is a constant, I just call this constant pi a. And then here also, this is a constant, and I call this constant here pi b, okay? And then I can write this here as just a constant b, and this here as we said this I can write in the form of t to the nth power. And then this here is, you know, kind of an exponential term. And you see the whole thing here now, it looks like an Arrhenius expression. It's b times t to the nth power times exponential minus, you know, this here divided by RT. And how to compute, I mean, if I tell you for each species what this pi a is and pi b, which are independent of temperature, I can just, you know, determine these for each species, then you can easily evaluate this. So that's what it is. I mean, here you have this, so we can write the equilibrium constant as b, t to the nth power times this exponential. This here is the reaction enthalpy. This n factor is, you know, just this here with this pi b, and this here is exponential and with this pi a. And these pi values, pi a and pi b, they are, you know, tabulated here in this you know, script that you can download from our webpage. And then here for, you know, many different species, and then you can just, you know, get these values from the table, plug it in, and you can compute the equilibrium constant as function of temperature, okay? And this shows an example here, green. We are not going to go through this example. This shows an example, N2 plus O2 goes to 2NO, okay? So you know, you have these pi values here, you know, you just plug them in. It's very easy. I mean, it's just this really back on the envelope. You don't even really need, except for this exponentially, I guess you need a calculator. And then at the end of the day, we get an expression here for the mole fraction of NO. And that's the result here. You see the mole fraction of NO then is constant here, t to the some power, very small power, so this is almost zero, and then here exponential function. But this value here, or the numerator, is very large. You know, I mean, this here would typical combustion temperatures, maybe 2,000 Kelvin, and then it's 10,000, so it's e to the minus 5. That's a large number. So, or a strong temperature dependence, let's say. So then we can evaluate this for different temperatures, and you see here at room temperature, first of all, we see in this, I mean, for equilibrium, we get a very low value, you know, 10 to the minus 10 ppm, parts per million, okay? So, which is 10 to the minus 16, very, very small. Was that to be expected? Yes, that was to be expected. Why? Because we're looking at the reaction N2 plus O2 goes to NO, right? In our atmosphere, we have N2 and we have O2. And the atmosphere, equilibrium is reached after a very long time. This atmosphere had about a few million of years, you know, to reach equilibrium. So if this is not equilibrium, it's only because whatever we changed in the, you know, past 1,000 years, but everything else is equilibrium. So if the equilibrium value was very high, then we couldn't survive because there's too much NO in the air, right? So we know NO must be really, really tiny. We know this without this, right? Okay, but then if we go to higher temperature, 300, 600, 1,000, 1,500, you see, you get a very, very strong increase here to about 1,000 ppm. 1,000 ppm, 2,000 ppm, that's the emission, the NO emission of a bad diesel engine from the 1990s. Okay, so that's a very large value. Today we don't want to have these large values anymore. So that's very large. And anyway, so if we look at this as function of temperature, then we can answer the question I raised yesterday. I said, why, you know, in combustion we form a lot of NO, and then in the catalyst it's consumed, even though the catalyst goes towards, I mean, the catalyst only makes things go faster towards equilibrium. And the answer is shown here, okay? So this is the mole fraction of NO as function of temperature. Or here in an Arrhenius plot, so this is low temperature, this is high temperature. During combustion, where the temperature is very high, the equilibrium value here is about 10,000 ppm, right? 10,000 ppm. Very, very high. So, but NO formation is a very slow process. We almost never reach the equilibrium in combustion. So, I mean, at least if we are smart combustion engineers. And so maybe you end up somewhere here. You never reach, but it goes towards equilibrium, but we never reach it. So let's say we're somewhere here. And then in the exhaust system, the temperature goes down, and with the temperature, also the equilibrium value of NO, okay? So then when the temperature is very low, then, I mean, maybe in the catalyst, we're somewhere here, then the equilibrium constant, or the equilibrium mole fraction is very, very low, and then, but the reactions, of course, they become very slow also. Now, actually, the equilibrium wants to consume NO and convert it back to N2 and O2, but the reactions become very slow. That's why we use a catalyst then and make the reaction faster so that we reach, that we get close to this equilibrium value. Okay? So that's you know, just using the equilibrium, and there's another thing I said yesterday. When you want to change, when you want to make a direction go in a, when you want to make a reaction go in a certain direction, you change the equilibrium. That's what you do. And so that's why it's so important to see, I mean, to be able to determine what the equilibrium is, to see under what conditions you get desirable, you know, conditions for what you want to achieve. And then the second example here is the equilibrium of this reaction, 2H2 plus O2 is H2O. Actually, if you look at this example for NO I showed you, it's very simple. It's very easy to follow through because we assume there that the concentration of N2 and O2 will never change because the formation of NO is really small. I mean, you don't consume much nitrogen. But here, of course, I mean, here you consume basically all the H2, all the O2, and you form H2O, so the concentration of the reactants, they change also. And one has to invoke here a few more conditions to determine the equilibrium composition, which then goes through, like we did in the past, which goes through the element mass fractions. Elements are conserved, and then you look at what do I have before and after and so on. So this here is a little more complicated, this example, and we just want to look at the result here. So this is the result. This reaction, we can evaluate again the equilibrium mole fraction or mass fractions here for different temperatures at 1 bar, and then also look at different pressures. And what's interesting is that, let's first look here at 1 bar, that if so at 2000 Kelvin, almost all the hydrogen and oxygen are converted to water. You know, almost complete conversion. The equilibrium constant is very high, okay? But if you then go to higher temperatures, 3,000, 4,000 Kelvin, it gets much, much less, okay? So higher temperature shifts the reaction to the reactants if the reaction is exothermic. This, of course, is an exothermic reaction. You know, burning hydrogen is exothermic. If you have an exothermic reaction, then increasing the temperature shifts the equilibrium to the reactants. And then if you look at the pressure, so let's look, for example, here at the higher temperature, 4,000 Kelvin at 1 bar, we get 0.4. At 10 bar, we get 0.6. So increasing the pressure increases the, or shifts the reaction to the products. Why is that here? Because this is a non-equimolar reaction. We have 3, let's say, moles or 3 molecules on the left-hand side, 2 molecules on the right-hand side. So if this reaction proceeds, you start out with a large number of molecules, and you go to a smaller number of molecules, which means the pressure in the system goes down, okay? I mean, for, let's say, a constant volume system. So you see a reaction that would decrease the pressure. If you increase the pressure, it shifts to the, to the products, which means it makes the pressure smaller. It wants to make the pressure smaller. And similarly here, if you make the temperature larger and it's exothermic, the reaction tries to make the temperature smaller again, okay? So that's what's called, this here on the next slide, that's what's called here the Le Chatelier's principle, is if you make a change, I mean, it's like, here chemistry is like little kids, or maybe like students, I don't know. If you make a change, the equilibrium always wants to do the opposite, okay? You want to make the temperature larger, and then the equilibrium does the opposite. You want to make the pressure larger, equilibrium does the opposite, okay? That's shown here also with numbers. I mean, I can, you know, this is how we approximated the equilibrium constant. I can take the derivative here, dk dt, and then for an exothermic reaction where the reaction enthalpy is negative, this change here also becomes negative, which means exactly what I just said. Equilibrium shifted towards the reactants when the temperature is increased, if you have an exothermic reaction. And here for the pressure dependence, here same thing also you can, I mean, this was the example we looked at earlier. You see that you increase the pressure, the reaction, that's not, yeah, the more reaction, this becomes smaller. And so again, that's what we call here the Le Chatelier's principle. The equilibrium always tries to counteract the imposed changes in temperature and pressure, okay? So you need to know, so for example, if you have an equimolar reaction, then the pressure doesn't do anything. The pressure doesn't change the equilibrium, but if you don't have an equimolar reaction, then it does, and similarly here with temperature. Okay? No questions about this? Then we go to the... Then actually we finish this part here of the thermodynamics part, and we go to the next section. You see here, the next section actually is governing equations. And as I said earlier, governing equations we're not going to discuss much because we use the equations here only in simple form, usually in simple form and in one-dimensional form, and if you and usually also with a few approximations. And so if you have a need to look at this, please go ahead and look at that section where all the equations are derived and so on. Okay, so then, what is this now? No. So this is the next section here. Now we're going to talk about flames. We're going to talk about laminar premixed flame, laminar premixed flames, and then laminar non-premixed flames. And the section on premixed flames, we have two different sections. One here is more on the kinematics of flames. How do flames propagate? And the second then is on the flame structure. You know, if you look with a microscope deep inside the flame, what's going on. And so here, so let's start with an introduction. Then we look at here the laminar burning velocity, and then we look at here an equation that describes how the dynamics of flames is the so-called level Z or G equation, and then we look at the effects of stretch on flame, the effect of stretch, which includes strain and curvature, and then we look at instabilities that happen in flame, which are very important, for example, when we talk about a high pressure combustion, or also when we talk about hydrogen. So most of these things I've said already yesterday. Premixed combustion, in premixed combustion, fuel and air are mixed, let's say perfectly mixed. Now, in most technical systems, the fuel and air might be pre-mixed, but maybe not, you know, perfectly pre-mixed. But here we will always assume it's perfectly pre-mixed. And then you have, you know, so let's say this is a gas turbine here. This upstream you have the swirler, then you have a swirler here. And typically, and then you have from the swirler, you have these passages that lead here into the combustor. And then you see the color is the velocity magnitude or so. And then this red surface here, that's the flame. And the flame tries to burn inside the unburned mixture. So everything here is burnt. And so premixed combustion then is used when you need high heat release. I showed you this yesterday. You get a lot more energy release or heat release per unit volume with premixed combustion. You know, that's helpful when you have small devices and when you need a low resonance time. But at the same time, really, maybe that's not even the main reason to use premixed combustion. Premixed combustion is always used when you want to reduce emissions, because you have different kinds of pollutants that you might form. Soot is one. Soot comes from rich conditions. And then the other one is nitric oxide, NO or NO2, or sometimes we call this NOx. And that is formed predominantly under very high temperatures. Okay? So if I have a premixed flame, I could actually run it lean, stoichiometric, or rich. Okay? You don't want to run it rich anyways, because if you run it rich, then you get, or maybe, yeah, I'll take this back. You might want to run it rich, but you might want to run it rich, but then, and then the temperatures are low, you know, are relatively low, but of course, rich conditions, you form soot, okay? And then stoichiometric, you form no soot, but the temperature is high, and so you form NO. Low, if you go very lean, then, you know, lean, you form no soot, and also temperatures are low because you have excess of air, and so you get very little NO, okay? So the strategy to avoid emissions is typically to go lean premixed. You know, that's what you try to do. For example, gas turbines, they're lean premixed, okay? I said earlier you don't want to burn rich, because if you burn rich, then, you know, there's fuel left over, or CO or hydrogen left over, which might be in the exhaust, and I took it back because you might want to burn rich in a multi-stage combustion situation, okay, where you first burn rich, and then you switch to, you know, add more air and then burn lean. So these are other strategies that are sometimes used, is to, you know, to burn rich and then lean to avoid stoichiometric conditions and burn off in the second stage the soot that was formed in the first stage, and so on. So anyways, so here in spark ignition engines, premixed, stationary gas turbines are premixed, and here smoke-free for lean premixed combustion, smoke-free, low NOx. But the disadvantage is, of course, anytime you premix, there's a danger that something explodes. If you would add the fuel here way upstream, the flame actually could burn back through the swirler into this region, and if you have a big volume here, the whole thing could just blow up. So these things happen once in a while. It's called flashback when the flame burns inside the mixing region. That's why the fuel is typically added, close enough, as close as possible to the exit. And then the other big issue, which we are not going to talk here about, but probably Professor Lewin will talk about when he comes Thursday, Friday, is combustion instability. I should say thermoacoustic combustion instabilities. We distinguish different instabilities. Thermoacoustic instability is something that depends on the whole system. And then we are talking about also about so-called intrinsic flame instabilities, which means instabilities only come from the flame itself, nothing to do with the surroundings. And so this is what we're going to talk about here. We talk about thermodiffusive and hydrodynamic instability. These are intrinsic instability. It just comes from the flame. Thermoacoustic instability, Professor, oh no, you are in my course. You're not going to his course. So what is a thermoacoustic instability is roughly this. Think of it like this. You have a fuel, so your fuel is added here. Air comes here from far upstream. They mix here and they start burning here. So let's say you have a pocket of fuel and air that comes into combustor, and then it burns. When it burns, there's a heat release, a volume change, and you get a pressure wave, okay? That pressure wave, it travels all the way downstream. It's reflected somewhere here at the exit. It comes back, and then it goes here maybe through this swirler. If it goes through the swirler, then, of course, you form very briefly, you form a higher pressure and then a lower pressure. When you have a higher pressure, the air flows a little more slowly, okay? And when you have a lower pressure, it goes faster. So you get, but let's say the fuel pressure drop is very large. Fuel is not affected very much by this. So then you get locally, you get a richer pocket and you get a leaner pocket. Now you have these rich lean pockets, they come in the combustor, and again, so sometimes you get a little more heat release and sometimes a little less. That sends out pressure wave. And now, talking back about the acoustic, the nonlinear feedback we talked about yesterday, if, this pressure wave now is exactly in phase with, the lean and rich pockets, then the next rich pocket you get is a little more rich. And the next one is yet more rich. It gives you a stronger pressure wave, and it makes the effect even stronger, okay? So that gives you, it's just like, again, when I go with my microphone to the loudspeaker, it amplifies. That's what we call thermoacoustic instability. It's an instability that comes from the flame, heat release, but interacting with the surroundings. You don't get these if you have an open flame. You need to have kind of a closed environment. So they get stronger for conditions, of course, where the heat release depends more strongly on the pressure, okay? You have a pressure oscillation, and if the heat release doesn't depend on pressure, it doesn't really matter. But if you have a very, very strong dependence, then you make pressure goes a little bit up, you get a lot more heat release, pressure goes a little bit down, you get a lot less heat release. And so that happens under lean condition. The leaner you go, the stronger this dependence. And that's the reason why, for this, I want to go as lean as possible because that reduces temperature and that reduces NOx. But if I go too lean, then this dependence of, burning rate with the pressure gets too strong, and I get these combustion instabilities. So there's a trade-off between low NOx and combustion instability, which means also if I understand and control combustion instability better, I can reduce NOx. That's really the purpose of controlling instabilities. And then, of course, I mean, here Professor Yedder, if anyone goes to his lecture in the morning, I mean, for rocket engines, these instabilities, they can be wild. In no time, the rocket just explodes because of this instability, okay? Nothing happens, the rocket engine is running, nothing happens, and then bam, gone, okay? So this goes really, really fast. Anyways, that's a big topic. These things I mentioned already. This shows here a laminar Bunsen flame. You get this Bunsen cone. This here is a turbulent premixed flame. You don't, you know, for diffusion flames, you get the yellow because of the soot radiation. Here, these are all lean or stoichiometric. You don't get any of this soot. And so here the blue and the blue-greenish comes from chemiluminescence, from excited radicals. That's what I mentioned yesterday. And then this is how the flame looks like roughly. So now we look at a flame. How does the flame look like inside? We look at a very simple kind of a view. And so I have this flame here, and now I'm showing species and temperature through the flame. On the inside of this cone here, everything's unburned. On the outside, it's burned, right? The cone tries to burn into the nozzle. And so here, inside the cone, in the unburned, I have oxygen, I have fuel, and then they're high and the temperature is low, okay? And then I have a flow that pushes these reactants towards the flame. You know, that's an advective flow or convection here. So pushes this towards the flame. Then downstream of this somewhere, I have the flame where all the reactions happen. And downstream of this, there's some equilibrium region where all, you know, everything is done and I just have high temperature, no fuel left, okay? So, but what happens in the reaction zone? The reaction zone, fuel and oxygen are consumed. So the reaction zone always keeps the reactants very small, okay? In the reaction zone, fuel in this case is 0 and oxygen is very small. In the unburned, upstream, you know, they are large. Inside the reaction zone, they're small. So there's a gradient in between. And because of that gradient, you get diffusion. And so it's like, you know, I mean, the reactants are like a car. You know, I have a car here, and it's on even slope. So I push the car. That's what convection does, you know. And then there's a hill, goes down. And then all of a sudden, I come to the edge, and then the car just goes by itself. Okay, that's exactly what happens here. Because so I have a diffusive flux of these reactants into the flame, and you know, that should actually make, I mean, if I have a flux here, it should make oxygen here go up and fuel go up, but the chemistry always keeps it down, always burns it, okay? So the way this works is that, okay, so let's move on here through this flame first. So here, the oxygen mass fraction goes down, and here also fuel goes down, not because of chemistry, it's just a diffusion profile, okay? So all of this is inert, nothing happens. And then at the same time, you have the temperature is very high here, it's very low here, which means I also here, I get a gradient, temperature gradient. You have temperature gradient, you get a flux, you get conduction, heat conduction, or I could also call it a diffusion of thermal energy. So this will preheat what happens here. This is all just diffusion. You preheat the flow, and then all of a sudden you reach a temperature here. We call this the ignition temperature, and we'll see later on what this really means. The ignition temperature, and that's when the reactions start. This here's the reaction rate, and then here fuel and oxygen are consumed. There's a transition here to burn temperature, and that's it. So let's see, right, at ignition temperature, I consume here the fuel that keeps the gradients always up and also keeps the temperature up. And then here in the burnt region, for a lean flame here, the fuel is completely consumed, and the remaining oxygen is left over, okay? And so this is how this works. You have reactants, they diffuse into the flame, or you could look at this in two steps. You have a fuel and air, which diffuses into the flame, and because of this, diffusion always makes gradients smaller, okay, and then they are consumed, and that makes the gradient large again, okay. So the reactions make sure the gradients are always large, and you have these diffusive fluxes. Okay, so that was just a simple picture of how a flame looks like. Now we can look at the dynamics or the kinematics of a flame. We said you have, if I have a premixed fuel-air mixture on this side and high temperature on that side, then in between I get this flame I just showed you, and that flame, it just burns into the unburnt region. So that is, something we saw here with this Bunsen burner. This shows a schematic of what I showed you yesterday. I have here comes the fuel. The fuel, is brought in here with a jet, which creates a low pressure region, which sucks in the air. It mixes, and then a premixed stream comes out. And then you have the flame that tries to burn inside. And you might remember yesterday when I turned down the fuel flow, then the fuel air mixture gets slower, and all of a sudden it goes plop, and the flame burns inside the burner, and then it's extinguished, right? Once everything is burnt away, there's just fresh gas coming in, which doesn't do anything. And if I would crank this up even more, then this cone would become more pointy, longer, and more pointy, okay? Right, so that's shown here. This here is this Bunsen cone, and you see here you have a slope here on the side. That right side of this flame is shown here then also. I have the flow here from the bottom coming in, and then you can actually, so this is VU, this is my unburnt velocity, and I can split this up into a tangential velocity, tangential to the flame, and a normal velocity to the flame. And then the flame, the burning velocity is nothing else. For a steady flame, the burning velocity then is exactly the normal component of the velocity, okay? And if I so let's say the burning velocity is always the same, for a given thermodynamic condition. If I crank up the velocity, then also the normal component gets larger, which means then the angle needs to change until the normal component is the same again, right? The smaller I make this angle, the more pointy this becomes, the smaller the normal component is. Okay, so that's what's shown here, and then basically I can measure the burning velocity. I can measure this experimentally. If I know the mass flow or the velocity coming in, I can measure optically, I can measure the angle, and then, you see here, measure the angle, is given here, and then here the burning velocity is the same, or the magnitude the same as this normal component, and the normal component is just the incoming velocity times the sine of this angle, okay? So if I know the angle, then I can determine the burning velocity. This, is one way how you can determine burning velocity, but it's not very accurate because of different reasons. First reason is this assumes here that the incoming velocity is homogeneous, a top hat profile. Typically, it's not the case because you have boundary layers, on the walls. Secondly, you see the flame here is anchored on the nozzle somehow, and which means you have heat losses to the nozzle. That also leads to inaccuracies and so on. So this is in principle something you could do. People have done this also, but it's not how this is done today. It's not accurate enough for the accuracy we want today. Now, in the flame front, here's another thing that's interesting. In the flame front, you have temperature increase, and the pressure is almost constant. So by, ideal gas equation of state, this tells you that the density must go down, okay? Temperature goes up, density goes down. And if I look at the mass balance through the flame, I have a mass flux that goes into the flame from the one side, I have a mass flux that goes out. The mass flux on a very small element of flame area, dm dot, is density times velocity, normal velocity, times the area. And so if I do this here, the mass balance would just goes in, just on the one side, just on the other side. If I assume the flame to be really, really thin, then rho times U times dA goes in, rho times U times dA comes out on the burnt side, the dA goes away, and then the unburnt density now is much larger than the burnt density, and so this means the burnt velocity needs to be much larger than the unburnt velocity. So you get an acceleration of the velocity. That's, of course, by the way, that's why you get explosions. That's why things explode, because, you just increase the velocity, okay? Or, well, I guess if it's enclosed, you increase the pressure first. Yeah, maybe it's more the pressure, but anyways, so you increase the velocity here, and that's interesting now because the normal velocity, it accelerates over the flame. The tangential velocity is the same, it doesn't do anything. And then you see that, the flame, the velocity comes in like this, but then because of the acceleration, the streamlines are deflected away from the center line, okay? And this here is this is a really, really nice image here by Godfrey Mangel from Stanford. These are overlaid. One is just here the flame, and the other one is here particles. And you see in the particles, first of all, the streamlines, how they come in, and then are deflected, from the center line. And secondly, also you see that the spacing between the particles, the individual images, this high-speed image, the spacing here is very small, and here is much larger. That shows you also the acceleration of these particles. Okay, so and then here's one other thing that's interesting about this flame. We said that you get this cone, and now if I decrease the velocity, the angle gets larger and larger until the flow velocity is exactly the burning velocity, and then it should be flat, and then if I decrease a little more, it starts burning into the burner, right? If I do the opposite, I make it larger, the flow velocity, then the angle becomes more pointy, or the angle becomes smaller, and the cone becomes more pointy, which means that the velocity is always larger than the burning velocity, right? The incoming velocity is always larger than the burning velocity, except exactly in the tip, okay? Because in the tip of the flame, the streamline is normal to the flame front, okay? So in the tip, the flame must burn faster than everywhere else. Interesting. And it must burn faster here by this factor 1 divided by the sine of alpha. Otherwise, it can't keep up. And that is an effect that is related to stretch, and the effect of stretch on the flame speed. And in fact, stretch, one reason it causes stretch is curvature. And you see you have a curvature here on top. And that curvature actually leads to the fact that, just the point just ahead of the flame, it will be preheated now, not just from downstream, it will be preheated from different sides. And that's why the flame burns faster there. Doesn't mean that happens for all fuels. For methane, this happens. For hydrogen, the opposite is the case. It would be slower in that region. And so that's why hydrogen flames, they're open. If you have a Bunsen flame, a lean hydrogen flame, it would be open. It's not closed on top because, it can't burn fast enough in the tip. Now, that, already hints at the fact that these stretch effects, they can, how curvature, for example, changes flame speed, that can be important, and so we are going to talk about this later also. Right, this, I think I just mentioned all of this. Okay, so we determined burning velocity that's a really important quantity that we need to worry about. Burning velocity, by the way, I mean, it's very important for safety. A fuel that burns very slowly is much safer than a fuel that burns very fast. So I mentioned we do some work to look at safety for refrigerants. The safety standards for refrigerants are really based on the laminar burning velocity, okay? So they say there's flammability. We talk about flammability also. Flammability is one, you know. I mean, how rich does a mixture have to be, a lean mixture have to be in order to be flammable? And then the second criterion they have is the burning velocity. They say if it's less than 10 centimeter per second, it's safer, it's one class safer than if the burning velocity is larger than 10 centimeter per second, okay? So for safety is very important. If we think of hydrogen, is a very dangerous fuel because burning velocity is very high. Hydrogen also, you know, is easy to get detonations with hydrogen and so on. So that's all based on the burning velocity. But then also burning velocity is important for, you know, stabilization. If I mentioned this, fuel flexibility of a nozzle or of a burner depends on burning velocity. If I have you know, I want it to be fuel flexible, I have one fuel that burns slowly, one burns fast, then it's very difficult to not have flashback, to not blow out the flame, okay? So for example, you know, we talk a lot about fuels like ammonia, hydrogen. Ammonia burns about 10 times slower than methane. Hydrogen about 10 times faster, okay? So if you want to cover that range with one burner, it's very difficult, and that's expressed by the burning velocity. And then also, burning velocity can be very important for efficiency. In a spark ignition engine, for example, you know this from your thermodynamics course, often we assume it's a constant volume process, okay? The heat release is at constant volume at top dead center when the piston is all the way up. If that is not the case, you know, if you don't get all the heat release at top dead center, the efficiency is less, okay? So fast burning is really good for spark ignition engines. And then also we'll see later on, another example is that flammability, you know, how lean you can burn a flame, also depends on the burning velocity. And in spark ignition engines also, you can increase efficiency by burning lean. If the leaner you go, the higher the efficiency is, okay? So, you can burn lean only up to a certain point, and then the burning velocity becomes so small that, you know, the whole thing becomes unstable, you know, it doesn't burn very well anymore and so on. So burning velocity is a really important quantity. And then, of course, also relating back to Professor Zarati's course, we use burning velocity to test and calibrate chemical models, okay? I mean, chemical reaction mechanisms. If we have a new fuel, first thing is we measure ignition delay time, burning velocity, and then try to understand if we can predict these global parameters. Okay, so I said in principle you could measure the burning velocity with a Bunsen burner, but we don't do this. And there are other ways to do this. One is to use a spherical chamber. And here's a point you might want to be mindful with. A lot of people call this a spherical bomb, okay? Don't call it, do me a favor, don't call it a bomb, okay? Bombs are supposed to disintegrate. This chamber is, you know, it's in the lab, it's not supposed to disintegrate. It's supposed to, you know, be there for a long time. So this is how this works. You have a spherical vessel, you have electrodes that meet up here in the center of the spherical vessel. You fill the vessel with a fuel-air mixture, you know, that you want to study under the thermodynamic conditions you want to study, and then you spark it here in the center, and then you get a spherical flame, and the spherical flame, it propagates, hopefully in a spherical, perfectly spherical way, and then you have optical access here. Typically, we do Schlieren imaging, and then you see how fast this propagates, and then from this you can determine the burning velocity. So this is then dRFDT. So this is the visible displacement speed that you see. That is related then here to, this is the displacement of the flame. It comes from two different effects. One is the flame burns with respect to the unburned, okay? But then the flow, there could also be a flow. Without burning, if you have a flow, the flame would also move, okay? So because of the burnt gases here in the center, and in the center, the velocity has to be 0 for symmetry reasons, the expansion the flow goes outside. So while this burns, you also induce a velocity here in the unburned, and that also carries the flame. Okay, but anyways, from this, you can determine then the unburned burning velocity as this displacement speed here times the density ratio, and that's shown on the next few slides how to do this, but this is what this is. So this is the laminar burning velocity, comma u. What means comma u? It means there's the burning velocity with respect to the unburned. If I have a flame here, and let's say it's stationary, let's say I have a flow of fuel air mixture comes from here, and then here's a premixed flame is stationary, and then the exhaust gas goes this way, right? Then we said earlier the exhaust gas is much faster than the unburned gas. And now, when I say the flame burns with a certain speed, then I have to say relative to the unburned or relative to the burned, okay? So the speed relative to the burned is much, much higher because the velocity is going away from this. And so the relative velocity between the flame and the exhaust gas is much higher than the relative velocity between the unburned gas and the flame. And so, anyways, typically when we say burning velocity, we always mean the burning velocity with respect to the unburned. And if we mean something else, we usually say this also. What's interesting here also, as I said earlier, the flame speed depends on the curvature. And so in the beginning here, just after ignition, you have super high curvature, right? And then when the flame grows, the curvature gets smaller, which means then the flame speed changes also. Really, we want to know the flame speed at 0 curvature. So what we do here, we record the flame speed, here this visible displacement speed, as function of the curvature, and then we extrapolate it to 0 curvature. Okay? So this shows an example here. This is a chamber that we run in our lab. Usually, there's a lot of insulation material around this also, but you see here the windows on the left and right side, here's schematic. This is here you have a little window, this is the window, and then this is the electrode. You have 2 electrodes that just come from one side and spark then here in the center, and then you put a spark there, and then you see, from the Schlieren image how this propagates. And again, this is actually what you see now, because in the burned, the velocity here is 0. In the unburned, the velocity, is large. It goes away from the flame. What you see here is the burning velocity with respect to the burned. Okay, so that's typically much higher than the burning velocity with respect to the unburned. Anyway, this here shows you how to, come up with this relation I mentioned earlier. We're not going through these details here. But, right, and so I mentioned there's a burning velocity with respect to the burned and unburned, and they are related here by the density ratio. The density ratio is about, at typical standard conditions for methane or so is about 7. Unburned temperature is 300 Kelvin, burnt temperature is 2,100 or 200, and then, so the density ratio is about 7. Which means, the methane has a burning velocity of, let's say, a little less than 40, And so with respect to the unburned, so with respect to the burned, it's 40 times 7, which is 280, almost 3 meters per second. So these two values, they're very, very different. Here's a fun thing about measuring burning velocities. One of the issues is, what happens if you, I mean, I said we're worried about sometimes refrigerants which are supposed to have very small burning velocity. And also, for example, if you go to gas turbines, you go to high pressure, we'll see later on, high pressure also gives you lower burning velocity, and then you want to burn really lean, gives you yet smaller burning velocity. What happens in this device when the burning velocity becomes very small? Then you spark, and then you have a little spherical flame, but it's hot inside and it's cold outside. And you get buoyancy. You know, this thing just moves up. And you see this here. Not playing. Here, you see this here. This is under normal gravity. This is some refrigerant, I can't remember what it was. I think it's R32. And you see now it lifts up, okay? And it forms like a mushroom type of a structure. You see this now. And anything I do here, you know, I cannot determine the burning velocity accurately, okay? Or let's say, any simple thing I do, I cannot determine the burning velocity. So we measure burning velocity under microgravity conditions. And for that, there's a drop tower here in Bremen, in Germany. And we have all the experiments in a capsule. And in the capsule, what they do is, here you see, capsule is in the bottom, and then they shoot it up, and then it goes all the way up, and then it turns around, comes down, and they move this little thing here with the what is this, polystyrene balls here, and then it falls into this thing, it decelerates here with minus 50 G, and then, you know, ready to do the next experiment. Takes a long time. I mean, for our experiments, we don't need that much time, so they lift it up. They don't shoot it up, they just lift it up to the top, and then they drop it, and we get about 4 seconds here of microgravity time. And that's enough for us. And then you see here 0G. I mean, this obviously stops playing, but it doesn't matter. But the 0G then is, of course, spherical because you don't have any gravity. So that's a fun thing to do. Usually what happens, you go there, you were planning. Actually, I think they're there now, or they were there last week. You plan a lot of things to do, and what happens is, you know, some mass flow controller doesn't work, and then is a problem. It takes a long time to do the experiment because they want to give you really, really good microgravity conditions, so they pull a vacuum in this thing also. Pulling a vacuum in this huge tower takes a long time. So now they put a second tower next to it where they don't pull the vacuum and they go very fast. You know, now it just goes up, down, very fast. So we have been using the new tower also, which is really good. And here's another one that's even more fun, is parabolic flights, okay? So we do experiments here with our colleagues, here Guillaume Legros from France and Fabien Holter from France, and here on this plane. And so the plane, it goes up, you know, flies a parabola, is a microgravity. You get 22 seconds here of microgravity, and then it goes down and turns around, and then you get almost equal time, 2G, okay? And it does this 5 times in a row, and then you get 5 minutes break to, you know, get your stomach in order, no, to get your experiment in order again. And then they do this 7 times. And so here, this is me. And I was perfectly happy, but after about 30 parabolas, I was thinking, okay, maybe I'm done now. But yeah, a lot of fun. Except, I mean, this. So you see, there are a lot of experiments here in this thing, and there's actually a chamber. You don't see it here. They have a little chamber where you can go inside and do whatever you want. I mean, you can do crazy stuff. It's busy though. There was actually on this flight here also there was some students from some high school. They also had a little experiment. And the only thing that I didn't like here is, you see, they had these really fancy suits where you look like an astronaut, and they also had the suits where you look like a mechanic. They gave me the mechanic suit. I wanted to have a, this cool suit also, but he's just the boss, Guillaume. He gets the cool suit. Okay, good. So that's a lot of fun that you can have also when doing combustion research. Now, if we look at another type of premixed flame that is often used is this flat flame on the so-called McKenna burner. The McKenna burner is actually kind of a porous structure that allows you then to have, because it's porous, high pressure drop, it gives you a kind of a top hat velocity profile, and then you get a flat flame downstream of this. And the flat flame actually, if the velocity is lower than the burning velocity, what happens is the flat flame, it burns now towards the burner. When it gets close enough to the burner, you will have heat losses to the burner. Heat losses make the burning velocity lower, so the flame will stabilize exactly in a point where the heat losses are so low that the burning velocity is exactly the incoming velocity, right? Now I decrease the velocity a little bit. Now it's too fast. It will go a little closer, more heat losses, makes it slower, everything's stable, right? So that's a stable setup. If I go the other way, but that does not give me the burning velocity because now I have heat losses, right? I mean, there is this heat flux method. There's another method to measure burning velocity. Heat flux method where they try to do this, but then they change the heat balance of the burner and so that it's exactly adiabatic, and then they measure with this also burning velocity. But that just on the side here. If I go the other way, I increase the velocity, then you go away, you get less and less heat losses to the burner. At some point, there should be no heat loss to the burner, and then it's just a freely propagating flame, right? But at that point, the flame could either sit here or it could sit there, because because the gradient is zero. So that's not stable. The flame doesn't have a stable position. So that you cannot really measure the burning velocity like this. Okay, so these burners here, these McKenna burners, they're often used to do measurements inside, to measure species, and one of the issues is, you can imagine already, I mean, you have a very thin flame. The very thin flame sits very close to the burner. I mean, how do you do measurements there? So very often people do these measurements under very low pressure, subatmospheric pressure, because if under subatmospheric pressure, the flame gets thicker, and then you have more space, okay? So you might see experiments in premixed flames under subatmospheric pressure, and you think, why in the world, I mean, we're interested in gas turbines. That's high pressure, or we're interested in whatever. I mean, many combustion applications are high pressure. No combustion application is low pressure, okay? But they do this, because it's easier to measure. But still it's difficult. You always have the burner and the flame, they interact very strongly. Now, but we can compute this. The nice thing about this is you see, I mean, this is, absolutely symmetric. And you can compute this in 1D, okay? Because there are no radial gradients, you compute this in 1D. So I can write the governing equations in 1D. The continuity equation, d rho dt. So let's say it's stationary, d rho dt goes away. And then plus d rho u dx plus d rho v dy. And because in here the y the parallel to the burner, nothing happens. It just reduces to this equation. And similarly here for the species equations, I get the convection term only in one direction. This is diffusion. Here J is the diffusive flux, and then there's the chemical source term. It's all 1D, and also temperature equation, I can write it in 1D. And so you see this first equation here. I can immediately integrate this. I integrate this from, let's say, the burner surface to some other point, or from just upstream of the flame to downstream of the flame, is shown here. And then I get rho u is just constant, that's what it says, and it's equal to rho u times SL with respect to the unburned. So that's how the burning velocity comes in, but rho u is constant. You look at this again, and this is a constant, this is a constant, okay? And it turns out that this system of equations is also overdetermined because these are second-order equations, right? So what is this? This is a system of ordinary differential equations, right? Ordinary differential equations means, it's not, the solution depends on only one independent coordinate, right? Which is x here in this case. No y and no z, okay? That's an ordinary differential equation. And then it's not a partial differential equation. And then it's a second-order equation because I have a second derivative. If I have only a first derivative, then I need one boundary condition. It's like an initial value problem, okay? So if I have, dy dt is equal to m dot divided by rho, then, I can compute what happens at time 2, but I have to give you an initial condition. So if you have a first derivative, you need one initial condition or boundary condition. If you have, we call it an initial condition, you have a second derivative, then you need 2 boundary conditions, okay? And so this is a second derivative here. We need 2 boundary conditions. What's the boundary condition? We specify the temperature in the unburned. And in the burned, we say the gradient has to go to 0, okay? These are 2 boundary conditions. But then at the same time, I also want the gradient in the unburned to be 0. The temperature gradient in the unburned should be 0. In the burned, it should be 0. And I want to specify the unburned temperature. So I have 3 conditions for a system of equations where I can specify only 2. Okay? So what happens then? How can I specify 3? Turns out there's a parameter in the system of equations that if I set the parameter just right, I give it just the right value, then I satisfy, with the 2 boundary conditions, I satisfy, all 3 boundary conditions. And so that is called an eigenvalue problem. Eigenvalue problem means the system is overdetermined, and I have an eigenvalue, and there's only one value assigned to this, that satisfies then all the boundary conditions. And that's, here in this case, rho u, or the burning velocity, that is the eigenvalue, okay? So that's how we, solve the system of equations. We solve it such that we satisfy 2 boundary conditions. Here with this, we assign 2 boundary conditions, and then the rho u is fixed so that the 3rd boundary condition is also satisfied. Okay, that's an eigenvalue problem. So when you solve these, it's not very difficult, but it's not entirely straightforward. One has to consider that. Okay, so that's what I just mentioned. So if we solve these equations then using Kempkin or Cantera or here the FlameMaster code, then you can compute burning velocities. You can compare them with measurements here, for example. And this just to show you, how do these burning velocities look like. This burning velocity here in centimeter per second for methane air at standard condition, 1 atmosphere, 300 Kelvin, as function here of the equivalence ratio. And you see that here roughly at stoichiometric, typically a little rich condition, you get the maximum, and the maximum here is about a little less than 40 centimeter per second. And then, if you go lean, then you get it goes down very strongly. The leaner you go, the stronger it goes down. And that's what I said earlier. Imagine you try to burn here at an equivalence ratio of 0.7, and you have an equivalence ratio that's just a little bit higher. You have this very high slope here, which means that it will burn much faster. If I go just a little leaner, it will burn much slower. So this high slope makes it very sensitive to changes in equivalence ratio. And then here also on the rich side, it gets much smaller. The values here, interesting also, at some point, you see a lot of measurements here, and you see also the range of measurements. Some maybe are a little older, some are newer, but there's always a range of measurements. They're not all the same because of experimental uncertainties. And then you see also here different models used to compute this. And then the models here also, they're all different. And the models, and interestingly, the models and the experiments, they cover about the same range, okay? This is what I meant earlier with calibration. You calibrate the models to somehow here predict, you know, what you measured. Now, okay, so that is that. And then the other thing you see is, you know, there's an equivalence ratio. If you go leaner, you don't have any measurements anymore, okay? So that's where you get close to the lean flammability limit, and we'll see later on, you know, what causes this. And then here, we have two different pressures. Again, here there's 1 bar, and then here's 5 bar, and you see if you increase the pressure, the burning velocity goes down, okay? And then here, so this is also shown here. This is the burning velocity for given equivalence ratio here of 1 as function of pressure. And you see it's roughly, see this log scale, this is log scale, this is log scale. So log scale means it's a power law dependence, right? I mean, it's SL is proportional to P to the nth power. Take the log on both sides, you get log SL is equal to n times log of pressure, right? So in the log-log plot, it should be linear. It's not exactly linear, but almost. It's almost power law. And then here, this shows different temperatures. And you see, of course, if you go to higher temperature, lower temperature here, higher temperature, it gets much faster. And that's expected also because, you know, chemistry, higher temperature always means things go exponentially faster, right? So, right. And then this here shows different fuels, methane. This here is heptane. I should have put in a plot here with ammonia and hydrogen. But so here is about 40, and heptane here also is about 40, you know, at standard conditions. I mean, they're very similar. Hydrocarbons are usually very similar. But here's hydrogen, and here you see hydrogen here at standard conditions like 250 or what. And this here was, you know, let's say a little more than 25. So it's roughly almost a factor of 10 difference. And if you go here to higher temperature, you get like 5 meters per second. And, you know, if you go to, but if you go to high pressure, then it also gets slower again. Anyways, and then this here shows, again, burning velocity as function of temperature, pressure for different temperatures. Why do I show this? Because, you know, I mean, most experiments for burning velocities have been done at 1 bar, 298 Kelvin. Is that really interesting? No, it's not very interesting. Well, yeah, okay, it's not totally uninteresting. But as I said earlier, very often we're worried about gas turbines, or we're worried about internal combustion engines. They're high temperature, high pressure, they're not ambient conditions, okay? Now, what's interesting is burning velocity. You go to high pressure, it goes down. You go to high temperature, it goes up, okay? So what happens, you know, when you do an isentropic compression, for example, like in a gas turbine, in a compressor of a gas turbine, or in an internal combustion engine. That's shown here. So this here is 298, 1 Kelvin. And this here just assumes isentropic compression with kappa, you know, 1.4. And then, let's say here, this is 20, pressure ratio of 20. And you see it's not very different. Here you have like 35, and here you have like 100, it's a factor of 3. Even though the pressure ratio is 20, okay? So that's because, you know, pressure and temperature, they roughly compensate, but of course, the pressure, if the temperature is exponential, so that's a little stronger. Okay, so keep that in mind, that, you know, for an isentropic compression, the burning velocity doesn't change all that much. Changes a little bit, but not all that much. So, I mean, we said burning velocity, when is the break, actually?